Where's my... I like the music. Yo, what up, Amog? Boy's finally here, dude. You here to get some help? Well, come speak. Come speak if you want. Drown gold or gay. What? Let's take from that. Bum 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 bum. Bum, 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 bum. Shifter, yeah, Shifter. We love Shifter, dude.
That's dope.
You got a new sound?
Yeah, he noticed, bro. You noticed, dude. Do you like this? That kind of cool, right?
I kind of like that.
So I have this thing. So it's actually kind of cool. I'll show you guys how this works. But I've been coding stuff in Ableton to now have it so that if I hit a certain button on my keyboard, it will play a random sound. So a random positive sound. Yeah, because I know you're I know you already have that one, right? But then like if I hit this button.
That's cool.
Yeah, I just hit this one button and it goes through all the random. It's cool. I figured out how to code it today. I realized I've been like kind of neglecting putting like cool things on the stream. Because I get like complacent. I'm like, it works. So, you know, let me just focus on teaching. But I'm like, no, let's spice it up, dude. Let's make stuff like kind of cool.
Nice.
Yeah. I gave my address. Where are you at, dude? Wow, Shifter's like, catch me in the streets, dude. I just need to figure out. I just need to figure out. I gotta figure out how the sustain works on it, though. That's the only problem. I hate having to like press this thing and then hold it down. That's like super annoying. I think I'll figure it out eventually. It's somewhere
I got a
here.
Spanish quarterly coming up tomorrow.
Uh-oh.
I meant Friday.
Spaniel. Spaniel's cool. I like Spaniel.
It's Espanol.
I have
Is that
serious
correct?
problems when it comes to schoolwork. Noise, what are your serious problems, dude? Tell us.
Ruh-roh. That is a son family friend. Oh, son of a biscuit.
What are the serious problems, Noise? Let us know. We're here for you.
So I'm playing laser game.
Give me access to soundboard. Trust me, I won't ear rape you. Yeah. No, yeah, I don't think you can use the soundboard with stages. I don't think you can do it with stages. I think in like regular ones you can. Laziness and getting halfway through and thinking fuck this and doing something else. Yeah, welcome to your generation, dude. Your generation is full of this shit, dude, because it's TikTok, man. You're just like, oh, I can just like do the next thing, scroll through the next thing. I don't like anytime you meet any bit of resistance, you're just like, whatever, do something else. But it's an important skill to have, you know. You're not always going to do things you like, so you're sometimes going to have to do things you don't like. I think persistence is the important thing. I'm not doing physics after that bullshit. Let me help you, Moog, dude. You said you were struggling in physics. You realize I have a fucking PhD in physics? Like, I teach a lot of physics. Like take advantage of the free knowledge that I give on this stream, please. And don't be like spaz messaging at like midnight being like, oh, Dr. Gold, this is due in 15 minutes. I don't get it. It's like, ask now, please. You know? Amog's teacher is an idiot. I don't think they're an idiot. I think there's some common sense in like the direction of gravity and whatnot that is being misunderstood and not taught entirely correctly. I don't think they're an idiot. Well, probably not the smartest person, but you know. Yeah, let me help you out with it at some point. Amog, let me help you. All right, cool. All right, here, let's start the stream off. Let's see what we got. All right. Welcome, everyone, to Office Hours. My name is Dr. Gold, Sack Education, the stream that helps you out with math homework, science homework, all sorts of stuff. We're here for you. Yes. Are those glasses real or for show? No, these are for show. Like I can do this. I can do this. Right? They're not really real. These used to be my real glasses before I got LASIK. So I'm kind of used to wearing them all the time. Yeah, I got LASIK, so I don't need glasses anymore. But I've been wearing glasses like all my life, so I'm kind of like used to it, I guess. That's how it works. Yeah. I'm kind of used to it. Okay, cool. Let's see. We got some help screenshots in the channel. Teacup, Ethan. Yeah, and Ethan, I said I would do the second half of his question. That's a good one. I'll try that one next time. Let me help out Noise first, because I haven't helped Noise in a while. And Noise hasn't asked for help, I guess. Is this something you actually need help with, Noise? It's like the 15th time she's wrong and I'm right. Yeah, I mean, it's okay. Your teachers aren't God. You know, they're gonna get things wrong sometimes. It's okay. Oh, you've done the question. Okay. Do you want me to help you with something that you haven't done, Noise? Like, how about like one of the physics things that you have due that you can't be fucked? You said like I don't want to do it. Ethan, we'll do your question probably next or something. Let me just see if there are people I haven't like helped in a while. I'm trying to help those people first. She has a PhD in shit and she's been teaching me for 7 years. Wow. Is it your mom or something? Dude, how do you have the same teacher for 7 years? She's been teaching... Oh, in general. Yeah. Okay. I mean, I've been teaching for a decade. I still make mistakes. You know, it happens. It's a thing. Good. Yeah, find an exam question on capacitance, Noise. Let me help you with that. I mean, if you've already done this, like, cool. Like, good job.
Nice. Yeah.
But let me help you with something you haven't done. I'm just trying to like make sure I help you guys the most that I can if possible. Amog, do you have another homework assignment that's due and maybe you want some help with? Some clarity? You actually love capacitance. Capacitance is cool. I agree. I like capacitance. I speedrun everything during lunch. Okay. The problem with that is you're not going to exactly learn things if you try to just speedrun through all your classes. Like, yeah, you're not going to remember it. And then you got the exam, and then you can't really speedrun the exam. It's plugging in equations? Yeah, okay. It's better if like you understand actually why you're plugging in equations rather than just, you know, a robot can like plug in equations, dude. It's you want to have like an actual connection with like what you're doing, so you actually understand what you're doing. Magnetic fields question? Sure, we can do that too. I'm down with that too. D equals V1T plus 1/2 AT squared. Yeah, that's a good equation. Yeah, that's a good kinematics equation. That's something actually I was doing with Ethan earlier. That was... Which one was it? Where was this one we were doing? That was this one. That's this equation basically right here. But I think, Amog, you have like some questions on like how it works. Like, I can tell conceptually you don't understand things because you start like getting worried about the direction of gravity, which like... You shouldn't be getting worried about that. Like, if you understand actually what's happening and aren't just blindly trusting the equations, the direction of things shouldn't really mess you up. You should be able to figure that out. You should be able to use common sense to know like which way is up and down. This is something that happens actually a lot in physics. If a lot of times you get kind of confused, like, wait, do I make this positive? Do I make this negative? And sometimes how the math works, you can't just blindly follow it because if you're using squares and square roots and whatnot, it'll force things to be positive regardless. And you have to kind of think in your head to be like, okay, wait, this thing is supposed to be negative, so let me just make it negative. But I know that's something that, you know, you want to just blindly plug in equations and whatnot, but that's not really learning. That's being a robot. That's just, you're not actually understanding what's going on. So, okay, here we go. For throwing ball up, negative gravity. That's right. Throw ball down, negative gravity. Yes, gravity always points down. Show me an example here. Show me an example where gravity does point down. This is called like a sign convention is what this is, you know? I could say that gravity pointing down is positive. It doesn't matter. Gravity does always point down. But whether, you know, let's say for instance you have like building here, right? And I have like ball, right? And I ask, you know, how far does the ball fall if it reaches the ground let's say it reaches the ground in 3 seconds, okay? This is good. I think this is probably like something that happens, okay? So, I know you're probably like blindly thinking, oh, yeah, let me use this equation, right? This what is this? D equals V1t plus 1/2 AT squared, right? This is the equation you know, right? Oh, t's not imaginary, but okay, watch. Yeah, okay. If t's imaginary, you're doing something wrong. Yeah, right? Something like this, okay? So you say, okay, cool. Well, initial velocity I know is 0, right? Because we're just dropping some shit, right? And then the question here becomes A, right? What is A, okay? So this depends on what your sign convention is, okay? If I'm calling this up and this down, okay, then A is equal to negative G. G is always a positive number. G is always just 9.8. Okay, that's a constant. Or 9.81 if you want to be like specific. But the positive or negative depends on which way it's pointing, right? If I call this negative and I call this positive, you get to call this whatever the fuck you want. It doesn't matter. You can call it whatever you want. Because then technically this D right here, this is technically X final minus X initial is what we say, is what it is, okay? That's really what D is displacement. So let's say we're calling down negative because this is what people usually do, right? Okay. Then this is equal to 1/2 times negative 9.8, right? Times t squared, okay? And where t here is going to be 3, so this is times 9. Great. So what is this? Do I really want to? Let me calculate this. I mean, you know what? No, fuck it. I'm just going to say that g equals 10 for now. Don't kill me. Just because I don't want, the point here is not actually to do calculations. It's to like show things. Negative 10, right? Okay. Times 9. Okay, so this would be equal to negative 45. So I would say x final minus x initial is equal to negative 45. And that makes sense, right? Because x final in this case, if I'm saying this way is down, this way is negative, this is 0. And that means x initial is 45, okay? Evening. But, okay, yes. So, displacement. So, yes, technically, the displacement is negative 45 because it started from here and it went down 45. That's why the displacement is negative 45. If you really want to say it, yeah, displacement equals negative 45, all right? But if she's asking how far does it fall, you're not going to say it fell negative 45. That's like saying I lost negative $3. Like, no. You lost $3. You didn't lose negative 3. So in this case, you would say it fell 45. The keyword is this word fall already implies negative. Yes. Well, no, it not because it's a distance, just because like it. I mean, I could have said how far does the ball rise? If I asked how far did the ball rise, then you would say negative 45 because rising is implying this direction. Yes, a loss of negative $3 is a gain of $3. That's correct. Yeah, exactly. Yeah, but because they said fall, yeah, it's like saying you have like $10 and then I don't know you spend $8 on I don't know what do you kids buy these days. I'm actually scared of what you guys buy these days. All right, let's just say you buy a candy bar. You say like I buy a candy bar of $8, right? I could say like, how much did you lose? And I would say, oh, you lost 8, right? I wouldn't, but technically what happened to your, like, the amount of money you have, right, is you technically went down negative 8. So, yeah, it has to do with that. Again, I could have switched this. I could be like, yo, wacky Jackie, dude, let's call this negative. Let's call this positive, right? Okay. And now things change, right? Okay. Because now gravity still points down. Gravity always points down, but now gravity points in the positive direction. So I would say that the acceleration is positive g. So this becomes positive this. And so now when I solve, I get positive 45. And so here, I get x minus x initial is positive 45. And then the reason for this, right, is because it went up 45, but up in this case is moving in the down direction. You have to kind of get used to, like, the numbers going up and down is separate to what the direction is. If I'm calling this direction positive, then something going up 45 means it's moving in this direction. If, for instance, right, I was calling this positive and this negative, then something moving in this direction is negative for displacement. That's the absolutes, if you want to start talking about the math and whatnot. But when you use t equals root d over 2, how do you have t equals root? How do you have negative gravity? You don't. So that acceleration always has to be positive. Okay, yeah, okay, I see what you're saying. So if for instance, yeah, if you use this equation, right, if you're just blind and like, okay, right, 1/2 at squared, right? In this case, t must also always equal the square root of 2d over a, right? So what happens is if the acceleration is negative, right? If, like, for instance, in this case, right here, right, where we said a was negative, the key thing here is that the displacement is also negative because you're technically going down. So displacement is the change in the position from the initial to the final, or it's really final minus initial. And so if you're going from a positive number, which is your initial, to a negative number, which is your final, a negative minus a positive is always a negative. So in this case, if this is negative g, this is also going to be negative. And that's why these two cancel out. And you end up getting a positive. You're right. You can't take square roots of negative numbers. It doesn't work. I think the problem is that you're not using Suvat. God damn it. I did that and I got it wrong. Show me where you got it wrong. Send me a screenshot. There's a lot in that thread. A lot of shit posting from Nick and stuff. So like I can't remember everything. I'm on my phone right now. Okay. Well, let me know when you get it on your phone. Anyways. Yeah. Show me where you got it wrong, and I'll give you a bond coin. Just show me. I'll count it as like part of your question per se. But you got to show me where you got it wrong. Okay. Did you find a question, Noise? Did you find a physics question I can help you with? Before I work on Ethan's question? It's starting to get hot in here. I linked you the exam. Did you DM it to me? Where'd you send it? Where? Oh, the Twitch chat. Oh, there it is. Okay, I see it. Okay, I was like, where the fuck did this go? Good, cool. All right. Ooh, okay. Magnetic flux density. You guys go like so extreme on this, dude. Dude, what? Webers, really? Ew. Hmm. This is a cool one. I like this one. I like the conceptual ones. I don't really want to do like heavy number ones right now. Like you, I can't be fucked. I like this one. This is a good one. Let me know right away if you already know the answer to this one. It's okay. Yeah, you're welcome, dude. You're welcome. For sure. Okay. So it says a short copper rod R, that's this thing right here, is placed on a pair of rails. This is like my railgun question. A horizontal magnet exists in the direction. Okay, so there's a magnetic field going this way. Cool, great. Diagram shows the apparatus would move directly from above. When switch S is closed, when we close this S, okay, what happens to R? Oh, okay, cool. Fleming's left-hand rule? What's Fleming's left-hand rule, dude? What? That's a thing. Excuse me? You Brits have, like, the weirdest shit sometimes, dude. What? Fleming's left-hand rule? Oh, F equals ILB. What? Oh, this is BI. Dude, this is too funny. You want to know where this comes from? This is actually kind of cool. I'm teaching noise where this comes from, actually. This is kind of cool. I've never seen Fleming's left-hand rule. In, like, my over a decade of teaching physics, I've never seen it called Fleming's left-hand rule. This is what we usually say. We say that F is equal to I. Technically, there's an L here. And then we say cross B. That's what we say. Or actually, usually what they do is they usually say I, and then they put a vector on the L times B. But this length of the wire and this current are usually, these are in the, what we say is like the same direction. So you could also write this as, if you say I is the vector instead, you could say this is equal to L, and then just say I cross B. If that makes any sense to you, it's because, like, you know, if you have a length of wire, right, that's pointing this way, I assume I also have the current pointing in the same direction. Okay. Okay. So we usually, this is a cross product, which usually you do with the right hand. Okay, so in this case, I would do this with the right hand. The difference between using the right hand and the left hand for cross products is their negatives, is what they are. So if you use the left hand for a cross product, you're technically doing, right here, you're technically doing negative B cross I, is what you're doing. Yeah. Oh, wait, let me think about how that works. Sorry. Yeah. This is technically negative B cross I. So what this converts to, so this is another cool product of, maybe you remember this, have you done anything with vectors and whatnot? There's some vector identities which are useful. So if I have A cross B, this is the same thing as negative B cross A. So if you ever switch the orders of the vectors in a cross product, you got to put a negative out front. So in this case, using the left hand is like automatically putting a negative in front of a cross product. This is equal to the same thing as positive I cross B, which is what this rule is. This is ILB, I cross B. That is so funny that they teach you a left hand version of this. Like, what? Really, we just learned this one. We just learned it's called the right hand. I don't know what it's actually called. But yeah, you just learned this one. And then this is a consequence of just, you know, making this thing negative, basically. Like, if you want to switch which finger is B and which finger is I, because that's all you're doing. Because remember, this is always like the C, and then this is like A cross B. But in this case, if you use your left hand, this is negative A cross B. And so if you want to switch them to B cross A, then you got to use the right hand. If that makes any sense, how that works. Yeah. That's so funny you guys learn that way. Okay, but anyways, all right. Okay, so what's going to happen here is, yes, we are suddenly going to have a current, right, that is going to flow in this direction, right, once I close the switch, because then I'm completing a circuit, right? Right? Oh, wait, sorry, that's in the wrong direction. It's this way, yeah. Okay. So there's actually a couple things that are happening here. Answer is A. Well, yeah, so if I use my right hand, I'm going to use my right hand here. So I is the index finger, right? B is towards the right. So the force will be up. Yeah, this will be upwards from the rails. Yeah, exactly. Yeah. If I wanted to, like, express that in, you know, this coordinate system, right? X, Y, or here, let's do it this way. X, Y, right? Z. Then what's happening is, so if you have I cross B, I is pointing in the negative Z hat direction. B is pointing in the X hat direction. And this is kind of another cool property of vectors here. Noise is that, so X hat cross Y hat equals Z hat. And then you can run these in like a round robin. So I can also say that Z hat cross X hat is equal to Y hat. And then Y hat cross Z hat is equal to X hat. So that's how they kind of run. So negative Z hat cross X is the same thing as X hat cross Z. Which will end up being negative Y hat. Because see, well here, let me see. Yeah. Z cross X would normally be in the Y hat direction, which would be into the page in this case. But since there's a negative out here, there's technically a negative here. So that means it points this way, negative Y hat, and that's why it comes out of the page. That's like the full explanation for it. Yeah. Cool. Good job, Teacup. Or not Teacup, sorry, Noise. I saw Teacup redeemed a bond coin, that's why I said Teacup. Love it. Okay. Yeah. Yeah, ask me more questions like that, Noise, dude. Like, you know, stuff that you haven't done yet. And then, because what I can do, Noise, is I can go more in depth to what, you know, what the science is behind it. And I think that hopefully will, or even more so, I can go into what, like, the maths is behind it, right? I hope this, like, helped you a little bit with, like, what the math is behind it. And then, like, some tricks with this. So that you can be more interested in it. I know you're kind of like, oh, fuck, well, the answer is this, whatever, I don't care. But, like, there's some cool math behind this, like, why it does what it does. And also, I learned, I didn't know that Fleming's left-hand rule was a thing. I think that's kind of cool. I prefer the vectors method. Yeah. If you want to do the vectors method, I can show you how to do the vectors method. You don't have to do funny things with your hands. You don't got to do hand stuff. Cool. All right, let's see. Ethan, are you here? I said I would do yours from last time. This is a good one, whoever asked this. I like this one. Falconer, how'd your stats go with this? Did you still need help with this? I can help you with this too. I know you were here, but then I think you had to leave because I went kind of late with another student. Ethan says, hold on. Okay. Holding on. Holding on. Yo, what's up? What's up, Ethan?
I'm doing fine.
Good to see you, dude. Did you do any trick-or-treating yesterday? It was Halloween.
I told you I was too old for that stuff, you know.
Oh, okay. I know someone else said that in the Discord. They said, like, what are you, like a child? And I was like, bro, what? I would go trick-or-treating. Free candy's free candy, dude. Need. Nerd. Nerd. Okay, Shifter. Be nice to nerds, dude. They'll be your boss one day, you know? Be your boss. Okay, cool. So what we were gonna do here, Ethan, is I was gonna like have you kind of go through this question again, but using the formulas instead.
Okay.
Yeah, okay, cool. Here, let me get past all this. Wow, we were doing a lot of stuff here. A lot of stuff. Okay, there we go. I was like, what the hell is going on? Okay. Let's see if you remember. I'm gonna kind of make you like redo part of these stuff because I want to like make sure you understand what's going on, right? It's always good to practice things again because it reinforces the concepts. Uh-oh. Ugh.
Right.
Are you there? Yeah.
I am.
Okay.
Cool.
Yeah, I can hear you.
Good.
Okay, so let's try to do this one again. So let's kind of go through what happens, right? They want us to use the formulas for distance in order to figure out how far this car goes. Previously, we used the area underneath a curve. We calculated the area, and that gave us the distance that it went. Because that's one way. If you ever find the area of a velocity versus time graph, you can find displacement. But this time they want us to use the formulas instead of just using areas. Okay. So let's maybe try to do this. Let's see here, right? We have a graph of the velocity of the car versus time, and I want to know how far it goes from this time point to this time point.
So I wasn't paying attention again. What?
Okay, we'll try to pay attention. I want to know how far the car goes from here to here, first off. Okay. How do you think we do that?
So we gotta identify which stuff we need to see, like
Good.
the formulas we'll use.
Okay.
So
Which one?
I can
Yeah.
already see one.
Mm-hmm.
So we see that the acceleration is equal to 2ms squared.
Good. Very good.
We write it down. Okay. And then the time seconds.
2 seconds. Good.
That's
10 seconds. 10 seconds. Sorry. 10 seconds.
Oh,
Yeah.
how about the 30? How about the 30?
Well, the same speed for 30 seconds. That's here. That's this time.
Okay.
Right. This is 30 seconds.
Okay, good.
We know this is 10 seconds.
All right. And I think the final velocity is 3 ms, right?
Why do you think it's 3?
It says it deaccelerates at the rate until stopping.
Well,
So
that's
it-
that's after the 30 seconds, though, Ethan. See, that's like it then travels at the same speed for 30 seconds. That's this portion, and then decelerates at this rate. That's an acceleration that has to do with this. That's what happens afterwards.
All right.
Okay.
All right. So basically, we're trying to find that one small part there.
Okay.
So we already have the acceleration and the time,
Good.
but I don't think I can find anything else.
Do you know what the initial velocity is?
They don't have here rest, okay? I don't see anything that has rest.
Well, do you see how it starts at 0?
Oh,
Yeah, it starts from
Okay.
the place. Yeah, so we assume the initial velocity here is 0.
all right.
Okay. So what can I use to
But yes,
find
so
what can I use to find the distance that this thing travels in the first part?
well, can we find the final velocity by using the first one?
Yeah, you can. Yeah, you can.
So can we solve that?
Yeah, how do you want to solve it?
So like we plug in what we know. So like VF is equal to VI plus A times T.
Good, very good. Yes, we can use this one. Okay, so I say VF is equal to VI plus A times T.
And so we plug in what we know. We are trying to find the final velocity, so that still remains unknown.
Good.
And so we know that the initial velocity is 0, which doesn't even matter.
0, go away, doesn't matter. Yep.
And then the acceleration is 2 and the time is 10. And if you multiply 2 times 10 is 20 for the final velocity.
Good, exactly. Good. Yes, very good. Yeah. So this whole thing right here becomes 20. Okay, so this is 20. Okay.
Yeah.
But what are we trying to figure out,
Yeah.
though, from the 0 to T1?
The distance.
Yes.
So that's when we gotta use one of the ones that has delta x.
Okay, good.
So we already have We already know the final velocity, initial velocity, the acceleration, and the time.
Mm-hmm.
And so what I'm thinking is that we use the fifth one.
1, 2, 3, 4, 5. Yeah, we can use this one if you want. Yeah, you can use this one.
Alright, so why don't we do it?
Okay, let's do it.
Also, I kind of like it when it's D better because delta X is kind of confusing.
Okay. So we have delta x, right?
Mhm.
This is actually a weird one. I usually don't use this one, but let's see if it probably works. So VF, which we know is 20. What's the time?
We know the time is 10 seconds.
Good. Minus.
5 times A, which is 2.
Good. 1/2 A, which is 2.
Times T squared, which is going to be 10 squared, which is 100.
Good. Good. Exactly. 100. Yeah. So if we do this, right, we get 200 minus 100. So that's equal to just 100, right? 100 meters. Which I think is the same amount that we had here at the beginning. Let's see. Let's see what we had here. Yeah. You see how we said 100 meters for the first part? By doing the area of this triangle?
Yeah.
Yeah, good. So yeah. You got the right answer, right?
Mm-hmm.
Okay. Good. So this is the first part. We got that done. So now let's try to do this part. Let's try to get the distance here.
All right.
What are we going to do?
So for the distance, this is where things will change, right?
Mm-hmm.
So, we still know that the acceleration is 2 because it still travels at the same speed.
No, when something travels... So let's think about what acceleration is, Ethan. Acceleration is when what is changing?
The speed, right?
Yes. Or when the velocity is changing. You have acceleration, really. Is the speed changing?
Well, no, because it says there
Okay,
travels
so
at the same speed for.
so what's the acceleration if the speed is not changing?
Isn't it just 2?
No? Let's remember, acceleration is how much the speed changes, right? It's technically defined as this. We say acceleration, we say that acceleration is the change in velocity over the change in time.
Hmm.
Okay. So if the velocity is not changing, right? What does that mean the acceleration is?
9.81, just like that or something?
No.
Or am I mixing that up?
What's the change in velocity if the velocity doesn't change?
Okay, this is really getting confusing now.
If the velocity does not change, what is the change in velocity? It's 0.
Same?
It's 0. 0. If something doesn't change, the change in it is 0. Does that make sense?
Not
Right.
really, no.
No? Okay, that's all right. All right. So delta V, whenever you see delta, this means final minus initial. Okay? So delta V is equal to V final minus V initial. Okay?
Yeah.
If we say something stays at the same speed, what does that mean about VF and VI? Are they the same? Are they different?
They're different?
No. I said something stays at the same speed.
The speed stays at the same speed.
So so that means this thing is the same as this, right? The initial speed is the same as the final speed. And we should be saying velocity, but yeah, whatever. Velocity and speed are the same thing here, basically. Okay. So if these two things are the same, what happens when you take a number divided by the same number?
It's just 1.
No. Something, sorry, what when you subtract something, when you take a number and you subtract it from the same thing.
Now you made a mistake there. No, it's a 0.
It's 0. Good, exactly. So do you see how the change in that, right, the change in velocity if the velocity does not change is 0? Does that make more sense? I know you
Oh,
said you were
yeah.
you said you were confused about it, so you know let me help you, right?
Yeah, I heard it.
Okay, cool. Okay, so if acceleration is the change in velocity, right? And the velocity does not change, what's the acceleration going to be?
Is it gonna be just 0?
Yes.
Because that's
Good.
the only logical thing I'm coming
Good.
up with.
Good. Good. Yes. Acceleration is 0 here, Ethan. There's no acceleration. Okay?
Right? Okay.
So if the initial velocity is 20, what is the final velocity? What's up, DM2?
The initial velocity is what?
If the initial velocity is 20 and the velocity doesn't change, what does that mean the final velocity is?
20. The same.
Good. Yes. Okay, so we know that this velocity is also 20. This is 20. Okay. How can we figure out the distance that it travels in portion 2 here?
Don't we use this? Don't we use one of the formulas?
We use one of the formulas. Which formula am I going to use?
Hold on. If we're trying to find the distance,
Yeah, we're trying to find the distance. Which one's that?
I'm thinking it's gonna be the fourth one.
Yeah, you can use the fourth one if you want. That's cool. Let's do it. Yeah, it works. Yeah, I'm cool with it. Let's use the fourth
So
one.
what's the underscore v thing?
That means V average. That's the average velocity. Whenever they put a bar here, this happens in statistics too. Anytime, for instance, you see like X bar, this is what's called the average. Average X is what they say.
Okay.
Yeah. Okay. So, and you can see this is the average velocity because it's 1/2 the initial and the final velocity added together. Do you remember how to like average two things together?
Up and then divide them by the same number. Like what I'm saying is that if you have two things, you add them up and then divide it by 2.
Exactly. Good. Yeah. So that's where this comes from. This is why they call this V average. All right. So we're gonna do 1/2. What's the initial velocity?
20.
Good. And then what's the final velocity?
20.
20. And then what's the time?
30.
30. Yes. Good.
Oh, yeah.
Good. So this is 30. Okay. So now we can just do some maths here, right? So this whole thing is just going to be
Alright.
20. Because 20 plus 20 is 40. And 40 divided by 2 is 20. And then we're going to multiply by 30.
Mhm.
So this is going to get me 600 meters. Okay?
Nice.
Huh?
Okay? So now I have that this portion, right? So we're going to say that delta x is equal to 600 meters. And if we go check that out, like let's see what we did on Monday. Let's see if it's the same. What do you see here? What distance did we get for the middle when we found the area?
600.
Yes. Good. See how we're getting the same answers?
Mhm.
It's kind of cool. This is what I like about physics is you can do things different ways and you get the same result. You know, there's not really a wrong way to do it as long as you get the right answer. Doesn't matter.
All right.
Okay, let's try to find this last bit here. This last area. We're gonna use we'll use your favorite color. We'll use blue for this one.
All right.
Okay, cool. Let's try to let's do the same technique here, Ethan, of like figuring things out.
All right. So
So-
here's what I'm thinking.
Yeah, what are you thinking? You're good.
I'm
Keep going.
thinking that the final velocity is 0 since it says of the trip and the 3 ms until stopping. So if it stops, it's at rest.
I would agree. I would say that the velocity is 0 here. Cool. And I would call this like V final, right? And then I would call this one like, let's say that like V initial here is 20, right?
It's still 20.
V initial here is 20, right? It starts at 20, right? And then it decelerates to 0.
All right. And then I'm thinking that the acceleration is -3 instead of just 3 because it says deaccelerates, which
It
means it's
decelerates.
stopping.
Good, yes. Decelerates is a negative acceleration. Good. So this is acceleration is equal to -3.
Mm-hmm.
Okay.
All right.
All right. What else do we need?
Do we need to find the one at the bottom since that's 10?
What's 10? Sorry. We don't know that this is 10
I
actually.
got-
We don't know that this is 10.
Okay, how are you so sure?
Well, because first of all, these distances look a lot different, right? This looks a lot longer than this.
Oh yeah. Mm-hmm.
Yeah. But there's a way to do it mathematically.
But yeah, I need to see. So we already have VI, VF, and A.
Uh-huh.
So I'm thinking. So here's what I'm thinking. I think we need to find a time. So I think we
Okay.
can use the first one.
Good. Exactly. Yeah, let's use this first equation right up here. Let's use this one. Okay?
So I already know that the VF is 0.
No, VF is 20. That's the Oh, so you're so right. Sorry. You're right. 0. Sorry. I make mistakes sometimes too.
Okay.
0.
Yeah, I've heard you made 2 mistakes.
I've made 2 mistakes today. I've made many mistakes in my life.
Anyways, yeah. So the VF is 0. The
Yep.
VI is 20.
Good.
And the acceleration is 3. It's not
Good.
minus 3.
Yeah, good. Very good.
All right, then you could just do like 0 is equal to 17t, right?
No. You want to move this over. This doesn't have a t on it, right? So I can't do 20t minus 3t 17t. I would need to move this all the way over first, right? Like over here. Yeah. And then just divide by 3, right?
Hmm.
So this ends up getting 6.67 for t.
How do you know this?
I just know what 20 divided by 3 is.
All right. So that's what we know of. And so since we have the time, we have VI, VF, A, and T.
Mm-hmm.
So all we need to do is find the distance.
Mm-hmm.
Which I'm thinking any of the equations 2, 4, or 5 could work. So I guess we could just go for number 5.
We can do number 5. You want to know something cool here? So you did need the time for an earlier part of this question, but do you see what would happen if I used the third equation? Do I need the time there?
Oh, no, you didn't.
You didn't, right? Yeah. So this is kind of a shortcut. Not many people know to use this equation, this one right here. But it helps when you're just like, oh, I don't need the time, right? So let's get some practice. Let's try using this one.
Okay, so if the time was unknown, then let's pretend the time was
Yeah,
unknown.
let's pretend we didn't figure out the time yet. Yeah.
All right. So VF is still 0, which is just 0, even though it's
0 squared. Good.
And the VI is 20, which is just gonna 20 squared, which is 400.
Mm-hmm.
And then we have plus 2 times A, which is -3.
Mm-hmm.
And then delta X is unknown.
Very good.
So
Okay.
we just gotta figure these out now. So 0 squared is just 0, 20 squared is 400, and that's -6.
Mm-hmm. Okay.
And now we can get rid of the 0 since that's nothing.
Mhm.
And then we move the 6 delta X to the other side.
Good. Very good. Very good, Ethan. Them up.
Divide by 6 on both sides.
Good.
Where delta X can be 11.
Yeah, good. So get rid of that. And then we're done, right? Just 400 divided by 6, which is 200 divided by 3, which is 66.7. That's what it is.
The 66.7.
Mhm.
Well, the other one there is 6.67.
Right. Well, let's see what we got on the other page. I think the other one we got 66.7. Yeah, you see how we got 66.7?
All right, then.
Same answer. Good job, Ethan. Good. Is that kind of cool, Ethan? You see how that works?
Yeah.
Yeah, nice, dude. Yeah. So hope that helps out, right? But that's showing there's two ways to do this question, right, Ethan? We could have done it doing the areas of a velocity versus time graph, or we could have done it using all the equations that we learned over here. Both ways work.
All right.
Nice, good. You're getting good practice with this, Ethan, which is going to help you when you have to do it later in your actual physics classes. It would be really good that you know how to do this. What I would say.
Right. Anything else today?
I think that's good for now. I think you learned a lot today. I think it's pretty good. If we have more time, I can teach you some more stuff. But I think I have a pretty big list of other students we got to go through. I think this was good. We got a lot done with this. I'm happy.
Oh, yeah, go ahead. Go ahead and do it.
Go ahead and do what?
Yeah, I'm back.
Go ahead and do your question.
Yes, we'll do. Okay. What's up, Justin? Justin, you ready to play? We're gonna play some Warzone today. You wanna play Warzone?
Yeah, I'm down.
I'm down.
Totally not about to ready to slam my desk in the amount of maybe a couple seconds.
Okay, cool, dude. How'd you do on your exponents test thing?
Exponents?
Or
yeah, I think I passed.
think you passed?
I think so.
Well,
At least I know.
Glad you passed, dude.
Actually, I think we already took the test. I don't know why I was worried about it. I think we already took the test that day.
What? Well, I hope you didn't, because you didn't know how to do it.
Give me a second. I'm gonna go scream something.
Okay. Give me a
And I'm
second.
back.
I'm gonna go scream something. Sorry, what?
Oh, yes.
All right, let's see.
I am in complete rage mode right now.
Why are you in rage mode, dude? What's going on?
I'm
What's up,
playing this
Pico?
goofy freaking laser game in Fortnite.
It's on page it's on page 223 of the PDF.
Thank you. Wait, 223 the PDF, or you mean of the textbook?
PDF as in like the Dropbox number 223. The actual like textbook page is 207.
I'm on page 223. It doesn't show up. That's weird. Whatever.
Let me see this. What page?
No, it's okay. It's okay. It's okay. I got it.
It's right there.
Wow. Ooh, this is a weird one. Okay. What does he want you to do? 53?
Yes.
Sketch the graph of V of t. Oh, in such a way that the water rises at a constant rate. Wow, that's cool. Okay. It's kind of a challenging question. I'm gonna have to put our big math thinker hat for this one. Oh, you already did this. Oh, you already got it. Okay, cool. All right. I think it's better with calculus. I think it's better with calculus too. Okay, water is pumped into a sphere of radius r at a variable rate such that the water rises at a constant rate. Let V of t be the volume of water in the tank. Sketch the graph. Where does the point of inflection occur? Okay. So, this is interesting. I have to relate what the volume of water is in this thing compared to the height of it, which I'm trying to think if I know what that is. As a maybe there's an equation for this. You're probably supposed to know this equation. Volume of a sphere with height. All right, night. Night noise. Night. Let me think. Not a triangle. This is work. Yeah, it's a partially filled sphere is what I want. The partial volume of a sphere. Yes, that's what I want. Oh god. Yep, this is what I want. Volume in terms of H and R. Volume in terms of A and H. A spherical cap. Very cool. I didn't know this. But okay. We could probably derive this equation from some form of calculus. I don't think we some calculus thing could probably do
It's a
this.
calculus textbook, so
Yeah. I mean, but you haven't really done integrals yet, so I think this is I don't think you've done integrals yet on this section. I don't think you have.
not that section, no.
So, yeah, you wouldn't know how to do this. You would have to have they have to give you that equation is what they have to do.
If you gotta do a lesson real quick.
Well, that would be kind of a longer lesson. I mean, I guess I probably could do it. Oh, here it is. Here it is.
Let's do the entire
Here it is. Here it is. Here. Do you see how they give it to you right here?
Oh, they
The
do.
volume of water here. Do you see how they say V is equal to pi r h squared
That's not
minus
the same
1/3 h
question.
cubed? Yeah, but they have to give you this equation. They need this equation.
Oh, it says continuation of exercise 53.
Yeah. Yeah. So they would give you this equation. You could derive this equation using integrals and calculus. But you haven't learned that yet in this part of the book. That's why. That's why we're not. Yeah, this right here, this equation right here. The volume of water is V equals pi RH squared minus 1/3 H cubed. Okay. It's a good thing to know. Yeah. Which I think is similar to what happens here. I think this is similar. This is volumes in terms of H and R. Because, all right, so they say the volume of this whole thing, I guess, is equal to this. But we want this part of the area, right? So this part, right, this like red part is like the whole sphere minus the blue part. So that would be 4/3. Let's just see if it's right. This would be 4/3 pi r cubed minus 1/3 pi h squared 3r. Sorry, this is also r. Big R. And then it'd be plus 1/3 pi h cubed because it's a minus and then another minus. So
This is weird.
it is weird. No, it is weird. It's so. The sphere has radius r. The volume of the water is V equals pi. Where is that coming from? I don't see that. Volume in terms of H and R. 1/3 pi H cubed 3R. Yeah. 1/3 pi H cubed. These two equations aren't equivalent. I can pull the pi out, so I have pi, and then this is 4/3 r cubed minus 1/3 h squared. Oh, so then there's a 1/3 and a 3, so this is just h squared r. And then this is plus 1/3 h cubed. Okay, this is very close. Very close, very close. It's flipped. And then there's this 4/3 pi r cubed that's wrong. Why is that? Why is that? Unless like I'm interpreting this thing wrong, probably. Oh, I think this is what they're saying. Ah, okay. They're talking about this volume. They're talking about the volume in the cap. Okay, cool. Okay, then yes. This equation does equate to this one. Okay, whatever. We're done. Cool. All right. Sorry. I thought they were talking about this volume, but they're talking about this volume. Okay. So it says water is pumped into a sphere at a variable rate. Okay, so that means that dv dt. What is dv dt equal to? Is dv dt 0 or is dv dt not 0?
dv. Wait, what?
dv dt. Yeah, is this 0 or not 0?
It would have to be not 0, right?
Why does it have to be not 0? I always say, dude, this one guy in my physics lab would always do this. He'd be like, so is it A or is it B? And, you know, you had a 50-50 shot because he'd be like, oh, it's B. And he'd be like, why is it B? And you're like, fuck, I actually have to explain why it is. Yes, okay. So you're correct that it's not 0. Good job.
Yeah, because of the...
But why is it not 0?
Yeah.
Because it's a sphere? No. Let's read the question. Water is pumped into the sphere at a variable rate, such that the water level. The air? What do you mean the air? What?
Like the air left.
No. So they say V is the volume of the water in the tank. Okay. What do they also say about the water? It's being pumped into the sphere at a variable rate, right?
I mean, it changes, so it's available at X or, I don't know, H,
Well-
H or AH.
Well, yeah, okay. So there's actually a couple implications here. So first of all, V is the volume of water in the sphere, right? Is that
Yeah.
volume changing? The volume of water in the sphere?
Volume of water in the sphere? No, the volume of the sphere is the same.
No. But the volume of the
water in
volume.
the sphere, that
is-
changes, yeah.
Good. That's why
It
DVD.
changes the sphere.
So DVDT is not 0. Is what we say, right? Because there is more volume of water being added to this. So the volume of water in the sphere is changing. We're not talking about the volume of the sphere. We're talking about the volume of the water in the sphere. Okay? More so, we say the rate that it's being put in, which is dVdt, we say that's also changing. So, what does that tell us about this? If maybe let's look.
We can get a better water pressure provided.
Well, it means the second derivative is also not 0. So
Yeah, 'cause they're
remember
both
that
variable rate.
this is the change in this. This is the change in the volume. The volume of the water is changing because we're adding water to the sphere. Okay, that's why this is not 0. And even more so, the rate at which we add water to the sphere, that's also changing. So that's why the second derivative is not 0. Okay? All right. Okay, so they want us to figure out what V is. They want us to figure out V, right?
V stands for
V stands for
virginity.
virginity. Okay. Okay, so this is pi.
Hey,
So here, we know that the volume, right, is equal to pi h squared r minus 1/3 pi h cubed. Okay? I think that's what was put in here, right? Pi h squared r minus 1/3 pi h cubed. Okay. And we're trying to figure out what's happening. So here's what they tell us. They tell us that the water level rises at a constant rate. Which variable here is the water level?
the variable of the water level.
Yeah. Yeah. Which variable is which variable describes how high the water is in the sphere?
H.
H.
Right.
Good. Okay. And then they say that the water level rises at a constant rate. Okay. So the rate that the water level rises, that's dH dt. Okay. Is that going to be 0 or not 0?
The rate, it would be not 0.
Not 0, because the height is changing, right? I'm adding water to this thing, so the height is most definitely changing.
It's
What about
going
What about, so we're going to say this is not equal to 0. What about the second derivative of the height?
volume? Oh no, you mean
So this is
that, like,
the change
after-
in this. This is the change in the rate of the height.
No, the rate of the height is changing.
No, the height is changing, but you see how they say the water level rises at a constant
Oh,
rate?
that would be 0.
Good, yes. Second derivative is 0. Okay.
My life's a lie.
It's okay. So this is what we know. We know d squared v dt squared. Well, we don't actually know what that is, right? But we do know that dv dt is also not equal to 0, right? Okay. All right. So I have a bunch of rates here, right? And I have this equation. So what do you think I need to do?
Okay, so we want to find the point. What the hell is the point of inflection?
Point of an inflection is where the second derivative is equal to 0. So
So
Point
like
of-
the middle.
yeah, point of inflection is d squared y dx squared is equal to 0. So the second derivative is equal to 0. Does this have any derivatives in it?
It has H.
But are any of these things derivatives?
Don't think so.
Right? Okay. Because it's rising. If it were 0, it would not rise. Yeah, you're right, Zorn. Yeah, sorry. I was just looking at the chat there. Yeah. If it were 0, if anything was 0, it wouldn't be changing, right? So dh dt 0 means the height's not changing. D squared h dt squared equaling to 0. That just says that the rate at which the height is changing is constant. This kind of goes also to like position, right? So velocity, let's remember, is dx dt. And then acceleration is dv dt, which is really equal to d squared x dt squared. Because it's the derivative of velocity. Velocity is the derivative of position. And so if something's moving at a constant velocity, if this is sorry, ooh, Jesus, what just happened? Okay. If velocity is constant, like if the rate at which something at the x position is changing is constant, then this ends up being 0, is what we say.
Okay.
Okay, yeah.
So if
okay.
the rate is constant 0.
If the rate is constant, if the rate of something changing is constant, then the derivative of that thing is 0, is what we say.
But if like it's changing, it would be not 0.
Exactly.
Okay.
Good. Okay. We know the height's changing. We know the volume's changing. That's why these two things are definitely not 0. But then they also tell us that the rate that the height changes is constant. If the rate
So that means that would be 0.
the rate of change is constant, then yes, that second derivative is 0. Because this is measuring how much does this change. If this thing is constant, it means it doesn't change. I went over this with Ethan earlier, right? Remember when I was doing like, what was I doing? I was teaching Ethan something here. Yeah, when I was teaching like acceleration, right? Is change in velocity over change in time. This is like the rate of position change, is what we would say. And if this rate is constant, right, that means this does not change. The velocity doesn't change. So the acceleration is 0, which is the second derivative, is what it is. Or the derivative of the rate. Okay. All right, so we have this equation, but none of this is in derivatives. You see how there are no derivatives here?
No, dude.
No derivatives. So what could I probably do here to try to make things have derivatives?
Harass it.
Yeah.
I really want to say integral for no reason at all, but it's not right. That's not even in this problem.
No, you want to derive each side. You want to start taking derivatives of both sides with respect to t.
Oh.
This is where implicit differentiation comes in. So this becomes dv dt. Okay, and let's see. Do we remember how to take these derivatives here? What does this become?
So we would do. We're looking for h, right? No, we're just doing all of it.
We're just doing all of it, but some things here, right? R is the radius. Does the radius of this sphere change?
No,
it's a constant.
So we don't
Good.
do that one.
So you don't need to do this one. You don't need to do pi, right? Pi is a constant too. Okay, so what do we do here with h?
You do h squared, we do 2h to the
Good.
1, and then we have minus 1/3 gh to the second.
Good, but then you also need to put a dh dt after each one, okay? So this becomes 2 pi rh, very good, dh dt, right? And then this becomes minus pi h squared dh dt. Really what I did is I did these. I just did the d's whatever, and then I just divided by dt. I know people are going to get mad at me, but like whatever, it works. Okay. Cool. And then okay, cool. So that's the first derivative, right? But I want to know what the second derivative is.
Second derivative.
So we got to derive again, right?
So we got the derivative of everything again. So
I know.
pretty much it's h again.
So this is d squared v dt squared, right?
So we would do.
Yeah.
So after we know that, so it's 2h all h dh over dt minus. So let's see. We'll put just doing h again. So
Well, so problem. Yeah, you probably haven't really learned this. This is now a product rule between two things. We have two things here. We have this and we have this, right? This is a and b. And when you have the derivative of a times b, this is dA dt times b plus dB dt times a. You got to do the derivative of one multiplied by the other plus the derivative of other plus the derivative of the next one times the second one. I know, it's a little confusing. So this is going to end up becoming, so you're right, the 2 pi r are all constants, okay? But now we're going to have dH dt, because we're going to do this. So the derivative of h is just 1, but then it's dH dt. So this is dH dt times dH dt plus the first one by itself times the second one, and that's going to be h d squared h dt squared, okay? And then the same thing's going to happen here. We're going to do minus pi. This is going to be 2h dH dt times dH dt plus h squared d squared h dt squared. This is probably confusing, Teacup. I understand why. Like, you're probably like, yo, what the hell just happened? Right?
It's exactly what's going on in my head
Okay,
right now.
here's what I'm going to say. Okay. We're going to call this thing A. I'm going to call this thing B. Because these things are constant. I don't care about these, right? Okay?
So we have a and b.
So when I take the derivative, in this case we're doing dt, okay, of A times B, this is equal to the derivative of this one times B.
And then plus derivative of b
Times-
times a.
Very good, Teacup. Yeah, exactly. This is called the product rule, is what it is. Okay?
Man.
So here's what happened. In this case, A was h, okay? So the derivative of h is just 1, but then it's dH dt. Or really, we can just say, right, you know, what's ddt of h? That's just dH dt. Okay? Do you see that?
Yeah.
Okay. And then we had to multiply it by b, which was already dH dt. So you get another dH dt there, right?
This is wild, and I
It
don't
is-
like it.
It's okay. This is cool. So then I do this times the derivative of the second thing, right? So the second thing was dH dt, right? So ddt of dH dt, this is equal to the second derivative of h, dt squared. This is why, for instance, we also put this exponent in between the two letters, is because like you're technically operating. It's weird. It's a math thing. It's a weird math thing. But this, hopefully, you see dt times dt, right? Is dt squared. But this times this is not dh squared, right? Because that would be the derivative of h squared. This is d squared, which means the second derivative of h. And then this just tells you what you're deriving it with respect to, which in this case is time. So that's why this one becomes a second derivative. And then this one, okay, right, times a, which is the same thing, which is just h. Okay? Now we get to here, right? Pi, okay, derivative of the first thing, right? What's the derivative of h squared?
Derivative of h squared.
Uh-huh.
2h.
Good. See where the 2h came? But then you need to multiply it by dh dt, right?
Yes.
And then you multiply by the other dh dt here, right? Because that's like times the b part. Okay, because this is a chain rule, is what this really is, okay? If I do d dt of h squared, right? Okay, let's say, I gotta think how this works. Sorry, d dt of h squared. This is equal to 2 times h times the derivative of what this thing is with respect to time is what it is. You could also think about it this way, okay? Let's say like just a is equal to h squared, okay? And let's do the implicit differentiation thing. You see how this is dA, right? And then this is 2h dh.
Mm-hmm.
All right, have a good night, Zorn. Sorry, it's kind of late. Okay. And then if I divide this by dt, right, dt, I get my 2h dh dt. And then this is the derivative of what the thing was with respect to t. I know, it's a little hard. Okay.
I was confused.
It's a chain rule. Right? You remember the chain rule, right? If I have something squared, right, that's 2 times something times the derivative of that thing.
Well, yeah.
That's literally what I'm doing here. I'm saying, okay, cool. This is 2 times h, right? Right? 2 times h times the derivative of what's inside, which was h, dh dt. Seeing a little bit more?
Yeah.
Okay. All right. And then it's, right, times the derivative of the second thing. So the derivative of the derivative is the second derivative. And then it's times what was left, which is just h squared. Okay. Okay. Some cool things here, though, right? We can start eliminating some shit. Because what did we say the second derivative of h was with respect to t? Teacup.
Hello?
Yeah. What did we say the second derivative of h was with respect to t?
It is derivative of h with respect to t.
D squared h. dt squared. The second derivative of
H
h.
squared h.
Uh-huh.
We said it was... Where is it? Is it just 0?
0. Yeah, good. So, look, anywhere I have a d squared h, that's going to go away.
Just 0.
Yeah, this goes away. See, this all goes away, which is nice. Okay.
Yay!
So now we're left with just 2 pi r dh dt squared minus 2 pi h dh dt squared, right?
Mm-hmm.
So this is equal to dh dt squared times 2 pi r minus 2 pi h. Okay?
Yeah.
Okay. Very cool here. Okay. All right. So when is this thing going to be equal to 0?
It would be equal to 0 when... Hold on. So we know that we want d squared h over d2 dt squared to get 0, right?
We want d squared v over dt squared to be 0. We want to know when this... So second derivative of v is all of this. I want to know when this, which is all of this, is equal to 0. You see how I have like 2 factors? So in order for this whole expression to be 0, I need either this thing to be 0 or this thing to be 0. Remember we had, like, for instance, like x plus 3 and like x minus 2 is equal to 0?
Oh god, do we have to do factor?
No, we've already factored it. It's already factored.
Oh.
You already have 2 factors. You just need
Yes.
one of them to be 0, right? In this case, we're like, oh, x is negative 3 or x is 2, right?
Okay, so...
So how can one of these factors be 0?
Would it be 2 pi r minus 2 r h to be 2 pi pi. No, that wouldn't be it.
Yeah. What would I need? First of all, what would I need for this to be 0?
Negative dh over dt.
No. You just need dHdt to equal 0, right?
Oh.
So you say, okay, cool. dHdt could equal 0. This would work out. But what did we say earlier up here?
It doesn't equal 0.
It doesn't equal 0, right? So that's not a valid solution, right? So this one doesn't work.
So it would have to be something with pi.
Yeah, so
It's pi one.
what would cause this to be 0?
If 2 pi r is equal to 2 r h.
Good. If 2 pi r equals 2 pi h, so what does that mean?
Math. It gets rid of it, and then we have r equals h.
Yes, good. There you go. So when r equals h, the second derivative is 0. So what that means here in term, like, I know, because we've been solving things in like algebra, calculus land, and you're like, what the hell do we actually just do? What we showed here, Teacup, right, is that when the height is equal to the radius, right, that's when we have an inflection point in the volume of water being put in.
If that was enough look, you have to put an equal sign.
Yeah. I'm pretty sure that's
We
correct.
did it.
I'm pretty sure it's just r equals h. What was this? 53? Yeah, I think we did it. What was this? Sorry, let me zoom out. I just want to see what page this was.
Do we gotta do like a question after this one now?
No, we're good for now. 4 point. That was a long
Friday,
one.
we're gonna have to do 54.
Let me see. What it was 4.4, number 53. Number 53. Okay. But they don't give the answer. What? Okay, here it goes. Cool. Do you see this? The point of inflection should occur when the water level is equal to the radius of the sphere. That's when r is equal to h. Isn't that cool? Teacup? Isn't that pretty cool? I think it's pretty cool. No? You don't think it's cool, Teacup? Okay, I think it's cool, Teacup. Anyways, okay, good. Awesome. Okay, cool. All right. Thank you, everyone, for coming to office hours today. Had a fun time with you guys. Wow, that was a long one. But yeah, I don't know. It's really cool. I learned a lot here. I hope you guys did learn a lot as well. Let me see. Today's Wednesday. Oh, that means we have our golden hour stream tomorrow. Oh, that's fun. Okay, cool. Okay. Let me turn this off. Okay. So, yeah. Our next stream is going to be tomorrow, Thursday. That's going to be at 4 p.m. Pacific. Sorry, no. Sorry, this one's an hour earlier. 3 p.m. Pacific, 5 p.m. Central, 6 p.m. Eastern. That's a great stream if you want to ask anything about, like, I don't know, life, politics, whatever's going on. Like, that is the stream for you. It's kind of more laid back. You can, talk about anything you want. The office hour streams are more geared towards, like, helping you directly with homework and stuff. But if you want to ask any other type of question, please, join us tomorrow during the golden hour stream. That's a fun one we like to do. Okay. It's Wednesday, so I'm going to do some Warhammer with the not Warhammer, sorry. I wish it was Warhammer. I'm going to do some Warzone with the students. So if you want to come play Warzone with us, we're going to do that in the actual gaming stream. You can just hang around. It'll take you over with the raid here. If you're in the Discord and you want to play Warzone with us, please come down to the recess voice chat, and we're going to do it down there. Cool? Sick. All right. I will see you guys tomorrow. Peace out. All right.